This webcast is going to talk about Newton's third law of motion and how to identify Newton's third law pairs of forces. Newton's third law tells us that all forces are created as a pair of forces. You cannot have a single force because every force is a result of an interaction between two objects. So if object B is applying a force on object A, well, then object A is also applying a force on object B. These pairs of forces are equal in magnitude, but they always point in opposite direction. Okay, let's do an example so that we can learn better how to identify those third law pairs. So we have a simple situation here where someone is pushing a grocery cart on a level floor, making it speed up. So we know the net force is not zero on this cart. Okay, and there is friction between the cart and the floor. Now, in order to see the third law pairs, I'm going to have to do more than one force diagram. That's because the pair of forces each act on different objects. And so you won't see a Newton's third law pair within the same force diagram. So I'm going to do 3 force diagrams, one for the cart, one for the person, and one for the earth / ground. They're really kind of the same thing. Okay, so I'm just going to set up to get ready to draw these force diagrams. And we'll begin with the forces on the cart. And so, we usually think, well, the cart has a weight. So there's a force of gravity that's being exerted on the cart by the earth. But any two objects that have mass exert a gravitational force on each other. Now, from our point of view, the weight of the cart is important to us because it would be heavy to lift, and if we do lift the cart up, we know it's going to fall down to the earth. But there is also a force of gravity that the cart is applying to the earth. There's a force of gravity on the earth by the cart. It's the same amount of force. It's just in the opposite direction. One reason that we don't worry about that so much is because that force is so small compared to the mass of the Earth that it has a negligible impact on the Earth. But I'm going to go ahead and put these little hearts here so that we recognize that these two forces are Newton's third law pairs. They are the same type of force. They involve an interaction between the same two objects, the earth and the cart, and they are the same amount. They are in opposite directions. Okay, let's see. The person is applying a force to the cart, making it move to the right. Well, when the person applies a force to the cart also applies a force to the person. These two forces, they are the same amount of force, but they are in opposite directions. And they are Newton's third law pairs. There is a frictional force being applied on the cart by the ground. And when any two objects that are rubbing against each other apply a frictional force on each other. And so similarly, there is a force of friction that's being applied to the ground by the cart. These two forces, they are the same amount of force, but they are in opposite directions. They are Newton's third law pairs. There's a normal force that the ground is applying to the cart. The cart is not falling through the ground because the ground is supporting the cart. And so there's a normal force there because they are pressed against each other. But just like the ground is supporting the cart's weight is pressing down into the ground. So there is a normal force being applied to the ground by the cart. And these are Newton's third law pairs. Okay, let's see. I think we've got all the forces on the cart. I'm going to put congruency marks on the normal force and the gravitational force because those two forces are equal. I know that because there is no vertical motion of the cart. Okay, let's go on to the person. So the person has a weight as well, right? There's the force of gravity being exerted on the person by the earth. And the person is also exerting a gravitational force on the earth. So those two forces are third law pairs. There's a normal force that is supporting the person. It's being applied by the ground, and the person's weight is pressing into the ground. So there's a normal force on the ground by the person. And those are Newton's third law pairs. So the cart is trying to pull the person to the left, right? See this applied force on the person by the cart? Why doesn't the person topple over when they get pushed to the left by the cart? It's because there's a force of friction that's opposing them, getting pushed to the left. So there's a friction force on the person by the ground. And therefore, there's a friction force on the ground by the person. And those are Newton's third law pairs. So I also know that the person is not moving vertically, and so the net force in the vertical direction is 0. So the normal force on the person and the gravitational force on the person must be balancing each other. Okay, so let's see, are we missing anything? I think we've done good. We have identified all of the forces in this scenario. Okay, so let's see what these questions ask. How does the size of the force that the person applies on the cart, so that would be the applied force on the cart by the person, how does that compare to the size of the applied force on the person by the cart? So you see that they're the same type of force. They're both applied forces, and they involve the same two objects interacting, right? But the force on the left is the force on the cart. The force on the right is the force on the person. So they are the same, except that they are in opposite directions. That's why I put this negative sign there, because the negative sign indicates it's going in the opposite direction. So these two forces are Newton's third law pairs. They are the same type of force, and involve the interaction of the same two objects. I'm running out of space. They are equal, but in opposite directions. Okay, then it says, how does the size of the frictional force on the cart by the floor, so that's frictional force on the cart by the floor, how does that compare to the frictional force on the person by the floor? Well, let's go up and look. We know the cart is speeding up as it moves to the right. Therefore, the net force is to the right. Therefore, the applied force that the person is applying to the cart must be larger than the frictional force that the ground is applying on the cart. In order for that applied force that the person is applying to the cart to be bigger, the frictional force that the ground is applying to the person must be larger than the frictional force that the ground is applying to the cart. So the frictional force on the cart is smaller than the frictional force on the person. And that's because the net force on the cart must point to the right if it is speeding up. And then it says identify all of the Newton's third law pairs. Well, they are the 7 pairs of forces identified above. Now I'll just go back up to look at that diagram. So notice that these pairs of forces, in order to see them, you always have to look at 2 different force diagrams. Because within a single force diagram, all of the forces are applied on the same object, right? For the force diagram of the cart is the recipient of every force. And so to see the third law pair, which would be applied to the other object in the interaction, you would have to look on one of the other force diagrams.